Quantum computing is a buzzword that's been thrown around a lot in recent years. We've all heard about how it promises to revolutionize current computational capabilities and achieve a so-called quantum advantage. But what really is it? What does it look like? In this three-part series, I'll be presenting a brief introduction to one of the most important quantum algorithms, the Quantum Fourier Transform. It forms the basis of many of the most well-known quantum algorithms, such as Shor's algorithm for integer factorization, the one that promises to break modern-day cryptography, or quantum phase estimation, a technique for estimating the eigenvalue of a unitary operator. Part 1 will be a general introduction to quantum circuits, from qubits to basic Pauli operators. Part 2 will be an introduction to a selection of quantum operators. Finally, Part 3 will be a capstone of what we have learned so far, where I will walk through the Quantum Fourier Transform. Throughout this presentation, I will focus mostly on the mathematics and formalism, such that you should be able to walk away from the series familiar with the core mathematics behind quantum computing. So, let's begin. First and foremost, what is a quantum circuit? This is an example of one. These horizontal lines represent qubits, the basic computational unit in quantum computing, exactly analogous to ordinary bits on a classical computer. These various squares that lie on these horizontal lines represent operations upon the respective qubit. These are known as gates, as we usually call them, in analogy with classical logic gates. The circuit diagram is read from left to right. This is the order of operations. On the right, we have measurement operations. These do exactly the same thing that we expect in normal quantum mechanics, where we take our quantum state and project it onto our measurement basis and take the mod square of the coefficients to give a probability. The results of these measurements are frequently written into classical bits or ancilla bits, but sometimes we don't explicitly state this. Nonetheless, the two most important building blocks are just the qubits and the gates. We will talk more about gates in part 2. For now, we will focus on qubits. In simple terms, a single qubit is just a complex vector in C2. For instance, we can write it out like this in the 1001 basis, where A and B are here complex coefficients. This is a pretty abstract representation. But fortunately, we can actually visualize this qubit fairly easily through an idea known as the Bloch sphere. To do so, we can take this complex 2 vector into a vector on real 3D space, R3, where we now use the XZ plane to represent the real 2 vector component and the y-axis the complex component. The reason we have a sphere then is because of normalization of the qubit state. Since it must have a norm of 1, the 3D vector must also always lie on the surface of this radius 1 Bloch sphere. The particular reason why we use a vector of length 2 is because we still want a 2-level system. We want to be able to output the classical 0 and 1 bits. You may recall that there is another really well-known system with such binary states, a spin-half system. It is thus very natural to associate the z-axis with the Pauli z operator, the x-axis with the Pauli x operator, and the y-axis with the Pauli y operator. It then also makes sense to assign the axes of the Bloch sphere with the eigenvectors of their respective Pauli matrices. The Pauli z eigensystem is so important that we call it the computational basis and give the eigenstates the names 0 and 1 in direct analogy to classical bits. On the Bloch sphere, these correspond to the up and down parts of the z-axis. Following this, the positive x-axis is the up x eigenstate, which we call plus, and the negative x-axis is the down x eigenstate, which we call minus. The y-eigenstates do not have special names as they show up fairly rarely, but the positive y-axis is nonetheless associated with the up y eigenstate and the negative with down y. So, to reiterate, the state of a qubit can be represented as a vector on this Bloch sphere. The default starting state is the 0 state, which is shown here as a red vector lying on the positive z-axis. In general, any state on the Bloch sphere can be expressed as some complex combination of the 0 and 1 states. To see this, we can use the polar representation, where we now have the regular spherical coordinates theta and phi, with theta being the angle of depression and phi being the azimuthal angle. From here, we can move around on the sphere. The plus state, or the positive x-axis, is when theta is equal to pi on 2 and phi is equal to 0, which is this linear combination. Rotating around the z-axis by pi on 2 then gives us the up y eigenstate, which is this, but with a complex I in front of the 1. Also, note how quantum computing is unitary. No matter how we move around on the sphere, we always have a normal 1. This is just like regular quantum mechanics. All of quantum computing is thus about moving this quantum state around on the sphere to a specific spot that we want. Now, back to the Z-eigenstates. The reason why we say that the Z-axis is important has to do with measurement. This is because, as we all know, we never get access to the actual complex amplitudes of a quantum state. We can only measure it to obtain some sort of probability distribution of classical states. In quantum computing, we choose the Z-axis as the basis of our measurement. This is the reason why we called it the computational basis. We end up with a classical probability distribution over 0 and 1, or classical qubit states. But only having a single qubit isn't very useful, just like how in normal classical computing, having a single bit is not very useful. What if we want to perform computations on more than one qubit? Well, we can expand our space by using tensor products to combine multiple qubits, just as we would for ordinary many-body quantum mechanics. In our case, to make a 2-qubit state, we would just simply take the tensor product of two 1-qubit states. And as such, when we make our measurement, we now have 4 possible computational outcomes: 0, 0, 0, 1, 1, 0, or 1, 1. In general, an n-qubit system will have 2 to the power of n configurations. This is precisely where quantum speedup comes from. By performing n manipulations, 1 upon each qubit, we actually act on 2 to the power of n classical bit configurations. Thus, as long as we can be smart and encode our problem in terms of this exponential configuration space, with some limitations, quantum computing can in theory drastically reduce our complexity scaling from exponential into polynomial. This finishes up our first video. Next, we will go into a discussion about gate operations on these quantum circuits.